This is the second lecture of the Introduction to Quantum Computing and Information. Um, in the previous lecture, yeah, let's review what we learned. Yeah, in the previous lecture, we learned two important concepts. One was the linear vector space, and another was the inner product. And then generally, linear vector space is kind of generalized from the familiar concept of the three-dimensional vector space, and then and most of the properties are yeah, very intuitive because we can generally imagine about the three-dimensional space. And there was a concept of the field, and then one of the of uh, uh, important property and then definition of the definition in the linear vector space is the linearly independent and the linearly dependent concept. And then that one is directly related to the definition of the dimensions of the vector space. And then also um, for the vector space, if we define the basis of the space, then every vector can be represented as the summation of um, linear combination of the basis vector, and then we call the coefficient of the linear expansion as the component of vector, and then once the basis, yeah, basis is not unique. For any given vector space, there are infinite combination of the basis, but once the basis is determined, then the component of vector is generally also fixed, and then um, it will be unique. Yes, for some given vector, for the given basis, the any arbitrary vector can be expanded as a linear combination of these bases, and then that expansion will be unique. And yeah, there are a few different examples of the vector space, not only the three-dimensional arrows, but n by n by m matrices might be a good vector space, and then function with some restriction will be a good vector space, and there will be tons of different examples. And another concept we covered in the previous lecture was the inner product. And then we, based on the concept of the inner product in the three-dimensional space, we generalized the requirement for the inner product. And these were for requirements for the inner product. And the first one is very obvious, and the second one is a little bit weird. Where we know that um, generally the inner product is symmetric, but we have to generalize for the complex value case, and then once the field for the vector field is generalized to the extended to the complex situation, then we have to be careful about the complex conjugation, and then it is called as a skew symmetry. And then the um, and yeah, and all the others are quite straightforward. And then in the next page, what I'm going to use is these two properties. One is the skew symmetry, and then another one is the linearity in cat. Maybe you are wondering why we had to define the generalized property of the inner product, and probably this might be one example. And yeah, and let's see how what we can do with such kind of property, such kind of definition. So let's begin our discussion, starting with what you are familiar with, yeah, which is the probably two-dimensional or three-dimensional vector, real space vector. So let's think about the two-dimensional vectors. So we might have some basis, and if we have any vectors like this one, then it will have some kind of coefficient. Let's say that if we call this one as a vector, then this will have, and if we call this one as x-axis and y-axis, then this will have x component and y component. And for this one, we would generally use the notation of the column vector. So well, there is nothing new in here, which is very, you are extremely familiar with this kind of notation. Then what can we do next? So if we have, yeah, for example, alpha w plus beta z cat, then what this means we will be probably that this will, as I mentioned in the previous lecture, this will correspond to the column vector. So this might have some kind of component, and this one also have some other different types of component, something like that. And then eventually, it is multiplied by some kind of scaling factor, and then their summation will turn out to be another column vector. So yeah, we know that the summation of these two cat will turn into another cat, which is the definition of the, and then that will align, that will be aligned with the definition of the vector space. So so far so good. And then for the new vector, we need some kind of notation. And then yeah, of course, we can still use the this current notation, but rather than using this one, probably yeah, we will just have something like this one, and this one will define the new result of this summation. So yeah, I will frequently use this kind of notation rather than just writing this one. Yeah, so and now the next question is, let's say that if we have this vector, yeah, and then this is a column vector. So assume that we have some kind of column vector whose component looks like I, and let's say yeah, I plus 1 plus I, yeah, some complex number component. Then we are also familiar with the concept of the transposing this column vector to the row vector. So if you are, if our given vector is some real space vector like that ax ay, then the corresponding row vector will be probably ax and ay. And my question is, then can we still use the same result with the vector that which has the its component as all of all or some of its components are complex number. And if we just follow the previous rule, then the corresponding row vector should be something like this one. And what I'm saying, and now what I'm going to prove is that it is actually not true. Yeah, so for the complex number, we cannot just transpose the column vector, but we actually also have to take the complex conjugation. So only when this one will transpose into 1 minus I, then this will be the correct row vector corresponding to the column vector. And also, moreover, the more important part is that what happens to this new summation vector. So I in the previous lecture, for any given cat vector, there will be always a corresponding bra vector, and it can be understood in terms of this column and row vector relation. So you might just think that, well, then the corresponding bra vector for this cat vector will be something like this one. And in the natural situation, you might just think that, well, then because this bra vector, this cat vector was the linear combination of these two vectors. So the corresponding cat vector will also have some component like this one, and then this one, the corresponding Prof vector for W and Z, and then the coefficient will still remain the same. And that's not correct. So yeah, what I'm going to do is prove that for this relation to be valid, then we need this kind of complex conjugation for each of the for each of these um, coefficient of the vector, and the proof goes like this. So the first thing we have to remember is that in the previous lecture and then in the review, in the previous page, I remind you about two properties of the generalized inner product. Um, the second property was that the number two was the skew symmetry. And what it said was if we have VW, then it is not the same as this one, but we need this complex conjugation. And another property we had was the linearity. And what linearity says was if we have this kind of alpha W plus beta X, then the result is V, sorry, VW plus beta Vx, something like this one. So this is just the definition of the generalized inner product. Then, yeah, using this one, we can actually prove that it should be complex conjugate of the alpha, not just the alpha here. And the proof goes in the following way. So the first thing is that from this linearity, we can say that um, the V V of alpha W plus B Z is because we decided to use this kind of notation. So this can be also rewritten as alpha W plus B Z. And from this linearity, we also know that this should be written as VW plus B times VZ. Now, yeah, on the other end, then what will be the value of the similar value like this one? But if we start with the sorry, yeah, I sometimes said I call this one as alpha and sometimes call it as A. Yeah, let's just use the A instead of the, oops, sorry, how about this? Yeah, let me just use A for consistency. So then what will be the value of this one? Well, then from the second skew symmetry, we know that this value can be rewritten as the following. So it should be almost symmetric to the original situation. Oh, I keep using alpha instead of A, like this one. But it is not just like that, but we should not forget about the complex conjugation. Then from this relation, we also know that that one will turn into A, and oops, yeah, here was a V. So yeah, this will be V W plus B times V Z, and then the complex conjugation of the entire thing. So Now, finally, yeah, we know that this complex conjugation will apply to all the scalars individually. And then we know that this might look like a vector. It is not, because this one is the inner product of the two vectors, actually bra and cat vectors, and then inner product of the bra and cat vector will turn into a scalar value. So what that means is that this complex conjugation will apply to each of the scalar value, which is a, and another scalar value for this one, and also for this one and this one individually. So what eventually this one will become is VW complex conjugation plus B times VZ, oh, sorry, B star VZ. However, now we can even simplify this situation because we know that by applying the skew symmetry one more time, then we can say that, well, they should be changed like W and V, and also for the same situation, this one can be exchanged with the Z and V. So, and of course, we can just stop here. Oops, I forgot to have the complex conjugation here. But we know that now we have common cat vector. So if we collect these terms with using the common factors, then eventually this one will turn into W plus B star, sorry, not, not V, but a Z. C, and they will be it will be the dot product with V. So from this one, yeah, by using this two property, number 2 and number 4 property, then we can prove that this vector corresponding to the original cat vector here, yeah, when this one is expanded, then the coefficient cannot be just to become like A and B, but they should be, we should use the complex conjugation of those vectors. And this is called as the antilinearity of the bra in the inner product. As you can see, yeah, we could prove that the antilinearity of the bra by using the generalized concept of the inner product. So that's the power of the abstract math. And now let's talk about the more properties of the linear vector space. So previously, if we didn't have the definition of the inner product, but only we had the concept of the vector space, then we could not talk about the length of the vector or the relation between two vectors. But now, because we have the concept of the inner product, then we can define what is the meaning of the orthogonality of two vectors, and the definition will become very simple. Yeah. So if we extend our concept of the orthogonality in the three-dimensional vector space, then we know that two orthogonal vectors should have a zero inner product. So whenever two inner product of two vectors vanishes, then we would call those two vectors are orthogonal or perpendicular to each other. And also with the definition of the inner generalized inner product, then we can also define the concept of the length of the vector. So we generally call the square root of the self inner product of the given vector, then we call it as a norm, and then that one also corresponds to the length of the vector, and it will become intuitive if you think about the definition of the length of the vector in the three-dimensional space. And finally, with these two concepts, length of the vector and then the orthogonality, we can also define what is the called as the orthonormal basis. And in the previous lecture, if when we only had the concept of the vector space, then we could define the basis concept. But in that case, basis doesn't necessarily need to be orthogonal to each other. So yeah, in the three-dimensional space, this kind of three um, three orthogonal vectors are very familiar to us, but in principle, there is no reason why we should choose this one as this one as basis in the three-dimensional space. In the extreme case, maybe this vector and another vector, maybe yeah, which is coming out of the page, then these three vectors probably will be a perfect basis in the three-dimensional space. However, nobody uses this kind of basis because it is somehow inconvenient to use in many of the calculations. So with the power of the concept of the inner product, then we could define the orthogonality and length concept, and finally we could define the orthonormal basis. And here also means the orthogonality to all the basis vectors will be orthogonal to each other, and then normal means that all of those basis vectors will have the length of 1. Now we define, because we define the concept of the orthonormal basis, then we can talk about the Gram-Schmidt theorem. Yeah, I'm sure that all of you, when you learn the linear algebra, all of you learned about the Gram-Schmidt theorem. And what the Gram-Schmidt theorem says is that even if you start with some bases which are not necessarily orthonormal initially, you can always find the orthonormal basis out of the non-orthonormal basis. And then the proof is quite straightforward. So I will leave it as an exercise for you so that you can prove the Gram-Schmidt theorem using the Pry and Cat notations. And once we know that we can always find out the orthonormal basis, then let's say that we just assume that we start with some orthonormal basis, and then one of the important properties of the orthonormal basis is that the um, the inner product between two not necessarily two, yeah, well, okay, I should still say two, yeah, and then if I select two of the um, basis out of the orthonormal basis, then the inner product between those two will be always either 0 or 1. And it will be 0 whenever you pick two different bases, and then they will become 1 if you pick the same basis twice. Then yeah, and then this relation can be written in terms of the Kronecker delta notation. And then now, if you go back to the last lecture, then we also claim that because of the concept of the linear space, linear vector space, then we know that the components of the vector will be always can be always uniquely determined for a given basis. But then at that time, we didn't show how we can find out those unique component of vectors. And still, yeah, generally, yeah, finding out the components of vector for some given basis might not be trivial for some cases, but if we focus only, if we turn our attention only to the orthonormal basis case, then the finding out the vector components becomes very trivial. And the way we can find out is the following, because we can imagine that well, maybe we can think about the three-dimensional vector space again, and if we have x, y, z component, and if you have any vector like some w, then then and then let me let me call this x basis as a number one basis, and y axis as a number two basis, and then a z axis as a number three basis. And then if I assume that all of those bases are also normal, then we know that the w can be written as the linear combination of maybe x1, well, let me use different notation. So this will be W1 in the one basis, and then W2 two basis, and then W3 in three basis. And then in this case, how can you find out W2? And as long as the 1, 2, 3 bases are also normal to each other, then the answer is simple. By just multiplying multiplying two bases on the W cat, then we know that this one, when this one is multiplied, I probably should not say call it as a multiplication, but probably it is easier to say. So it is actually taking the inner product between two bases and one. Then because they are also orthogonal, so W1 will this term will just become zero, and also when two is applied to uh, basis 2 is applied to basis 3, then this term will also become 0. So just by taking the inner product between the basis number 2 and then W vector, then we will end up with just W2. So that's so as long as the all the uh, as long as the bases are also normal, then the finding out the vector component is very simple, and then it can be always generalized in this way. Then the next question is, what happens if we have two vectors? So previously we had only one vector, but now we can think about another vector, and then let's call it as a v. Then the question is, and then we know that this v vector can be also expanded in terms of the um, 1, 2, 3 orthonormal basis. So it will look like this one. Then how can we find out the inner product between the V and W? And then yeah, so yeah, they can be always written in. They can be always expanded in terms of the basis, like this one. Then what is the what is the inner product between those two? And then in this case, now you should remember the anti-linearity property of the Bra vector. So instead of multiplying v sub I directly, you always have to take the um, complex conjugation of each of these components, and then you will end up multiplying each of these also normal bases to the um, these also normal bases. But we know that because of this chronicle delta property of the inner product between the orthonormal bases, they will it will actually reduce into the chronicle delta function, and then that means that this double sum will become single sum like this one, and then the result of the inner product becomes becomes like this and then it becomes very simple. So this is the kind of the definition. You can use. This is not the definition, but because as long as you expand two vectors using the same basis, yeah, if the bases are not the same, and then those bases should be also normal, and then if the used bases are not also normal, then you cannot obtain this kind of result. So make sure that you are using the same orthonormal basis for the expansion. And as long as you stick to that requirement, then the inner product between those two vectors will become as simple as like this one. And so from now on, we will just use this definition of the inner product between two vectors. And now it becomes obvious why we had to define the skew symmetry instead of just the regular symmetry. And then if we define if we required only the symmetry rather than the skew symmetry for the inner product, then the problem is the following. For example, if we have this v vector as the I times 1, and then all other terms are 0, then the norm of the same vector v will be just yeah. So with the with this property, then it will becomes like a minus I times I, so it will be plus 1, and then it will be larger, either larger or 0, larger or equal to 0. However, if we didn't have the skew symmetry, and then in this case, we won't have this component. We won't have this complex conjugation for one of the um, factor in the this product. That means that we won't have this minus sign here in front of that. Then yeah, you will just end up with I squared, which will turn into minus 1 rather than plus 1. And then this relation cannot be satisfied. So if we did not define the symmetry as a skew symmetry rather than the regular symmetry, then yeah, we won't have this positive semi-definite property. And then the concept of the norm becomes very weird, because we are using the concept of the norm as the length of the vector, but then what's the meaning of the um, complex numbered length? Yeah, so that is a, there is a problem conceptually. So that's why we prefer the skew symmetry rather than the symmetry for the complex vector space over complex field. Now, if we generalize what we learned in the previous page, then we can say that whenever we have the v and w vectors, and then when we find out their components in some given vector, then these components will be uniquely determined, and then we can always write down the component of this vector. For example, for this vector, yeah, we can just instead of writing it as the linear combination of the many cat bases, we can just write down only the components in a column vector. And also similarly for the W, yeah, we can just write down in this way. And by writing down this way, then we found out that the inner product between v vector and v bra vector and w cat vector, their inner product will always look like this one, and then this one can be easily represented by the corresponding row vector and then column vector. And in this case, what you should be really careful is that whenever you are converting the cat vector to a corresponding bra vector, make sure that you always take not only taking the transpose of the matrix, but you should also always take the complex conjugation of each of the individual components. Yeah, so if you forget this one, yeah, then you will have a lot of trouble. Yeah, as you saw in the previous at the end of the last previous page, that the norm might become negative. Yeah, which doesn't make sense at all. or norm actually will become complex number. Yeah. And then so yeah, whenever yeah, so yeah, from now on we will map the cat vector to a column vector, and then we will map the bra vector to a row vector. But whenever we are converting from the cat vector to a bra vector, yeah, don't forget about the complex conjugation. And we call that the overall process as the transpose conjugation, or sometimes it will be called as adjoint operation. And also it will be sometimes called as a Hermitian conjugate. So let me summarize how the rule for taking the adjoint operation. So assume that we have some linear equation relating the cats or bras, and then whenever you are taking the adjoint of the linear equation, then what you should do is, if your linear equation is composed of the cats only, then every cat should be replaced by its corresponding bra. And then what you should not, uh, what you should be careful is, when you are taking the bras, make sure that you also take the complex conjugation of all the coefficients. So for example, if you start with um, some vectors like um, yeah, like um, alpha and 1 plus beta 2, then whenever you are taking the adjoint, then not only this one will turn into the bra, but everything. Yeah, so this one cat will become bra, and then at that time alpha should become the complex conjugation, and then also the um, two cat will become two bra, and then at the same time the coefficient will become the complex conjugate of its own value. So, and then again, when we are taking the adjoint of this bra, then everything will become reversed. Yeah, so that is the rule you should not forget. And then you can also now, yeah, you can also prove that whenever we are taking the adjoint of the um, whenever we are converting the cat to the bra, then we can also prove the entire linearity by using this rule. So in the previous page, we learned that um, this vector, this cat vector, can be represented as the column vector like this one. Then the multiplication of the scalar will be multiplied to each of the component like this one. But then whenever we are taking the adjoint operation, then we know that each of the component, yeah, this one will be transposed. But at the same time, each of the components should be um, each of the we should take the complex conjugation of the corresponding values like this one. And then finally, if we just collect the common factors of A star, then it will become the remaining part will be just will be the remaining part will correspond to the um, bra vector of the original vector, and then the common vector will be A star, which is the complex conjugation. So that's another way to prove that whenever we have this kind of relation, then yeah, we should not forget about taking the complex conjugation of the coefficient. And yeah, again, yeah, this result is keep repeating. Yeah, so they are the adjoint relation of each other. In linear algebra, there are many interesting theorems which can be derived from only a few basic properties of the linear vector space. And then one of the famous theorem is the Schwarz inequality. And I'm sure that most of you already learned the Schwarz inequality in the previous linear algebra class. But let me just derive this result using the bracket notation. So this will be a good exercise for the bracket notation. So let's begin. Yeah, first, let's think about the intuitive meaning of the Schwarz inequality. What it really says is that it's the following. So let's assume that we have two vectors. Yeah, something like this vector. Yeah, this is the real vector in the two-dimensional space, something like this one. Well, it doesn't really have to be in the two-dimensional space, but yeah, just for the simplicity of the discussion, yeah, let me just assume that it is in the two-dimensional space. Then we know that the inner product between these two vectors will have the component of the angle between these two vectors. So we know that um, the inner product between these will become the absolute value of the each of the vector, and then it will be cosine theta. So because cosine theta is the absolute value of the cosine theta will become like this one, and then it will be from 0 to 1. So yeah, it can be easy. We can easily see the relation of this Schwarz inequality. Now, um, we no longer can use this intuitive concept because our definition of the vector is in the abstract linear vector space. So we cannot use any of these geometric concept, but then we should still prove this relation using only the using only the definitions we obtained so far. So how can we proceed um, the proof? And we will still use some concepts as shown in this intuitive derivation. So first thing is that yeah, again, let me just call this one as a abstract vector of called as a W, and then let me call this one as a vector cat vector V. Then we can think about the component of a V in terms of the one component which is parallel to the W vector, and another component which is um, yeah, which is orthogonal to the W vector. Then how can we find out this vector and this vector? And let me call this component as the Y vector, and then this component as a Z vector. Then how can you find out the Y component? Then Y component is the projection of the V vector on the on this W vector. Then how can you find out the projection? Yeah, for the to find out the projection, what we should do is first calculate the normalized W. So let me call that one as a W bar. Then to normalize some vector, normalize means that it will be parallel to the original vector, but the length will be 1. So to find out such kind of vector, then what we have to do is calculate the length of the original vector, and then I have to um, find that, yeah, and then I have to actually take the square root of the this one. So square root, and then W. Then with this kind of definition, then the length of this vector will be 1, and then the still this vector will be parallel. So um, Yeah, so this is the unit vector along the vector v. Then to find out y can be simply found by taking the inner product between that normalized w and the original v. Then y can be still can be found by well, actually, y is not found by this one. What I'm doing is only the calculating the length of this y vector. So yeah, I probably should not say equal to y. Yes, sorry. So what I'm calculating the um, length of the y vector. Yeah, let me just roughly say write in using this notation. So it is w hat um, multiplied by a v, and this will become square root of w, and because now it is the bra of this cat, so it will be w bra and then v. And finally, if I want to find out y vector, then I have to multiply the um, unit unit vector along w, which is w hat. And the length of this y vector is already found by using this one. So it is the product of this one and this one. And now we have in the denominator, we have the 2 square root of this. So yeah, the denominator will become just w. And then in the numerator, I have this component, which is the w v, and then I have this component, which is this one. So that this is the kind of definition of the y. And then how can you find out z vector? It is simple because it is the um, component of z component of v vector when we subtract this one. So it is v minus y, and now it is v minus w v over w w and w. Okay, so that is the definition of the z. Then what we are going to do is that we are going to calculate the norm of the z. And when it is the norm, yes, so not okay, not necessarily norm, but what I'm doing is calculating the self inner product of z. So we know that this one, whatever z is, it should be always the larger, either larger or equal to 0. So yeah, eventually we at the end of the day we will use this relation. But before we use that relation, let's find out the z z inner product. Then now this one, the bra, is we should first find out the bra, and then to find out the bra, then we have to use the cat relation. So to find out the bra, then there will be v minus, and then this is scalar value, and this is also another scalar value. So what we have to do is take the complex conjugation. But we know that the W self inner product is the real value. So yeah, we don't have to worry about taking the complex conjugation. However, for this one is this might be a complex value. So we have to take the complex conjugate of this scalar value, and then complex conjugation of this one can be just found by using the skew symmetry. So just switching the the location of the W and V like this one. And finally, for this guy, it will be W bra. So that is the corresponding for this one. And then for the rest of the part, it is just a copy of the above one. So W, W, and W, V, and W. And now if I multiply all of them, yeah, distribute this one to on each of the term, then the first term is VV and minus, and in the numerator WV inner product and W W, and V is multiplied on this guy, so that is the VW. So yeah, I multiply V on both terms, and now yeah, multiply this one on this term, then it will be minus VW over WW, and this one will multiply on here. So WV, and finally, the entire part will be multiplied on here. So there will be plus, and then in the denominator, we will have the square of the WW, and then in the numerator, we have the multiplication of this scalar value and this scalar value, which is VW and WV, and finally we have the WW, which is WW. So we have a square of WW in the denominator, and here we have this one, so they will just cancel with each other. Now finally we have this VV, and yeah, we know that this is scalar value and this is scalar, and also scalar. So even though the order is different, and then we can just swap the order, then that means that each of them, this term and this term has the same value. So it is twice of the VW multiplied by WV over WW. And finally, we have this term, but you will note that this term is the same as this one, because this square is cancelled by this guy. So, and now it is plus rather than minus. So this 2 will become just a plus 1. Not plus 1, just a minus 1 only. So this is the result of the ZZ value. And then we said that ZZ, the inner product, self inner product of the vector should be either larger or larger than or equal to 0. So that is the final result. And if we move this one to on the other side, that means that V multiplied by W should be smaller or equal to VW WV. But we know that these two guys are complex conjugation of each other. So this can be also rewritten as VW absolute value squared, and this side is they can be also written as the um, V absolute value squared, and then this can be also norm of the W squared. So yeah, that's and then with this result, we can prove that this Schwarz inequality. Yeah, so I intentionally showed you how to derive this Schwarz inequality using the abstract linear algebra, and then using the bra and cat notation. And then it is a little bit lengthy, but you can always reduce some of the middle step. But the point is, bracket notation is very convenient in proving this relation. And another popular theorem is the triangular theorem, a triangular inequality. And I can also derive this relation by myself, but I think it is better, it will be a good exercise for you. So I will leave it as a homework for you. Another important concept in linear algebra is the subspace. And then subspace can be understood in terms of uh, by using the three-dimensional space and the two-dimensional space as an example. As we can consider about the three-dimensional space, then we know that any vector inside the three-dimensional space can be can be decomposed into three x, y, z component. Or on the other hand, we can say that the entire three-dimensional space can be spanned by three orthogonal bases like um, um, x vector with the unit length and the y vector with the same unit length and so forth. And then, yeah, even though the three-dimensional space is a well-defined vector space, linear vector space, we also know that any vector inside the xy plane, where this two-dimensional space, that is a very good. So any vector in this xy plane are the vectors in the well-defined vector space again. But now the dimension of the of xy plane is only 2, while the entire three-dimensional space has the dimension of 3. So in this case, we call this xy plane as a subspace of the entire three-dimensional space. And then in that case, and also another good space. Yeah, so if I call this three-dimensional space as the V space, then we know that this one has the two-dimensional space, and then we might say that it is orthogonal to and then let's say that let me call this xy plane as a one subspace, and this 2 means the dimension of 2. And in this three-dimensional space, we also have additional subspace where you might also consider xy as a two-dimensional subspace, or um, xz as another two-dimensional space, and so forth. And then they are not only limited to xy, xz, or yz, but you can always think about any other two-dimensional space in the three-dimensional space, and then they will be all of them are well-defined, good, well-defined subspace of the three-dimensional space. And we might also consider that another space we can think about is the one-dimensional space, which is parallel to the z-axis. So yeah, in that case, the space by itself might be boring, but that is also very well-defined space. And then maybe I can say that it is one-dimensional subspace, and then it is parallel to the z-axis, or we might call this xy subspace as a two-dimensional space, and it is orthogonal to the z z direction. So yeah, there will be many different ways to define the subspace, but and then this subspace will be also an essential concept in linear vector space, and also in the quantum mechanics. Now, let's think about what is called as a linear operator in linear algebra. Um, yeah, we can think about the linear algebra as a matrix, as you are familiar with. We know we are well aware of the multiplication of the matrix and the vector. And then, for example, they generally goes like this. So whenever we have some column vector, let's say a three-dimensional column vector, and maybe we can think about 2 by 3 matrix, something like this one. Then the result of multiplication will be will become like two-dimensional vector. So you might just consider this one as the multiplication of the matrix on the vector, but on the other hand, we can think about this kind of relation as a mapping of the vectors. What do I mean by that? For example, let's say that our starting point or the input. I will call this one as an input vector space. Then, yeah, we know that any arbitrary vector inside this three-dimensional space will be mapped by this matrix, and then it will be transformed into a two-dimensional vector space, and then yeah, it will become I don't know which one it will become. It will be, but basically the role of this matrix is mapping of that matrix sorry, the mapping of that original vector to a new vector, and then I will call this one as an output vector space. Then I will call this transformation as a omega, and then we can think that the original vector is represented by v, and then the resulting vector or output vector is represented as a v prime. Then we, in principle, we yes, and so in this class, yeah, or in quantum mechanics, we are using this kind of notation. So v prime is transformed from v through the omega operator. So this is the kind of definition of the linear operator in the or meaning of the linear operator in the quantum mechanics. And then here, as we discussed here, in general idea of the linear operator, yeah, generally the input vector space and the output vector space doesn't have to be the same. For example, here the obvious example is the input vector space was the three-dimensional space, and the output vector space might be two-dimensional space. So they are, in principle, are distinct. And also another example might be that even with the same three-dimensional space, for example, one of the vector might be the vector, the input vector might be the vector inside my office, and then the output vector might be a vector in your room. In that case, the dimensions are the same, but the two vector spaces are completely separate from each other. So the linear operator by itself can transform any vector in different space. However, in this quantum mechanics, we will consider that, or in this class, at least we will consider that the input vector space and the output vector space are the same vector space. So that might be more natural because we don't live in different world because we are living in the same world. So input vector space and the output vector will be still in the same vector space. But while I'm explaining many things, I might just use this kind of separate input vector space and output vector space for clear explanation. But yeah, whenever I'm drawing different input and output vector space, just assume that they actually imply the same thing. Yeah, the main reason I might use a different vector space is I'm considering using different bases, and then to represent a different basis rather than just drawing everything in the same coordinates. I might just use the separate coordinate like this. So as I mentioned, we are only considering the same vector space for the input and output vector space. And then the next thing is that a linear operator can also act on the bra. And then in that case, we will just write in this way. So if I just use the same analogy to the matrix multiplication, then we know that if we have some instead of having using this case, this 2 by 3 matrix multiply on the column vector, we might also consider another row vector um, uh, being multiplied to the matrix. Another two-dimensional vector is multiplied on the 2 by 3 matrix, then output the output result will become three-dimensional result. So in this case, the bra, yeah. So I mentioned that the bra vector corresponds to the row vector, and so row vector will be transformed to another row vector or another bra, yeah, through the linear operator or matrix or whatever you want to call it. And what I explained up to this point is about the general operator. Yeah, so operator is mapping some vector from one space into another vector in another different space, and then now we are going to narrow down our interest onto the linear operator. So then that means that linear operator requires additional condition, and then one requirement is that so this is not necessarily only for the linear operator by itself, but whenever we are calling something as a linear, then the following two conditions are the requirement for the linear thing. Yeah, so the first thing is if the input is scaled by alpha, a factor of alpha, then the result will be also scaled by the same factor of alpha. Yeah, so that sounds very reasonable. And another requirement is that if the input is the linear combination of two things, yeah, something like this one, then the output will be also scaled by the same factor, and then their addition will be still maintained. So these are the two conditions for the linear property. And of course, you might consider that this one is a special case of this one. So maybe you can think this one as a single requirement. But whatever you want to think about it, that these are the if you want to call something as a linear, then these are the basic idea for the linear property. And of course, we are also consider the linear operator acting on the bra. So the same similar relation should be also hold for the bra case. Then now, because we decided to not only decided, but because the quantum mechanics works only in the linear operator fashion, so yeah, that is actually a very good thing for many of the situation, because whenever we have a linear operator, we have a nice property that as long as how does each of the basis vector will be transformed by the given linear operator, then we can immediately predict what will happen to any arbitrary vectors. And then the proof can be written in this way. Yeah, but let me just redraw in other board. So if it was not a linear operator, then typically, even if we have two-dimensional space or whatever space, and then just assume that they are the two different space, and then if it is not linear, then we know that this vector might be mapped might might be transformed to some vector here. Yeah. So and then another vector might be transformed to another vector, and then a new vector might be also mapped by mapped to some also other vectors. And if there is no linearity condition, then there is no guarantee that the information of how this vector and then this vector is transformed to these two doesn't necessarily imply anything about what will happen to this one, because it can be completely arbitrary. However, once we have the linearity condition, situation is completely different. For example, if I have if I have if I know that how this one vector will be transformed to new vector in the output space, and then I will call it as a one prime, and then this is another basis 2, and then if I know that how this number 2 vector will be transformed to new vector, and then I will call it as 2 prime, then now we know a lot of things, because whenever we have the input vector, which is the summation of the uh, v1 1 plus uh, so they can be always written as the linear combination of these two basis vector, and then uh, from the linear property of the operator, that means that omega v means that that will be omega 1, and v2 is v2 omega 2. However, yeah, so this is only valid. This relation is only valid because omega is a linear operator, and then we know that we already calculated that the this one vector will be transformed will be mapped to one prime vector through this omega. So we can simply say that, yeah, this will be always like this one, and then v2 is always like this one. So yeah, from this relation, we can claim that only by knowing how one vector will be mapped to what, and then two vector will be mapped to which vector, then the rest of the calculation does not require the entire calculation of all the vector inside this vector space, but it is simply the remapping or rewriting the original coefficient of the um, input vector into the new vector inside the new output space, but you don't have to change any of these v1 and v2. So that's the power of the linear operator. Another property we have to consider is how can we define the product of two operators? And then yeah, this is simply a definition. So when we have two operator, um, uh, so when you are given lambda and omega operator, and then if we if we define the lambda multiplied by omega, then what do we mean by multiplying those two operator? And the answer is simple. So that's why I use the symbol for the definition. So this is just defined as that whenever you have a product of multiple operator, then what that means is that we should first act this omega on the vector first. Then the next operator will work on the entire result of this operation. So and then sometimes we will use this notation to represent that the result of this operator are working on this vector. So this is simply the definition of the product of the two operators. And then from this property, we can also derive many interesting results. Another interesting property of the linear operator is the something called as not the property, but the definition is the commutator. And commutator is generally defined in this way. And then you might wonder what's the difference between these two. And then, but as I mentioned in the previous page, whenever we have this kind of product of two operators, then the thing you have to remember is that this one will operate on the some vector, and then whenever we have some vector following behind this one, then for example, if I have the commutator of the acting on the vector v, then just by following the definition, this is the definition. This is the meaning of the commutator, and what it really means is that for the first term, V will first work on, and then later omega will work on. While for the second term, omega will first work, and then later this one. And then if this is some kind of scalar function, well, even in that case, the order might be matter, but might matter. But in general, um, this becomes more obvious. The difference between this term and this term becomes more obvious when you remember that the operator generally corresponds to um, a matrix. So yeah, for example, you are familiar with the concept that the multiplication of AB is not necessarily the same as the BA when A and B are the matrix. So in that case, the order of um, the operating order matters, and then then the commutator might be considered that the role of the commutator is measuring the difference between this case and then this case. And based on these definition, there is some interesting properties of or identities of the commutator, and it can be easily proven. So let's see. So to prove this relation, what we should do is just to follow the regular definition of everything. So if we just follow the definition of the left hand side, then what that means is that omega lambda theta minus lambda theta omega. So that's all it says for the right hand side. And then what we should do is the following. So what we can do is that we add some word terms between these two, and then the first thing I can do is add lambda omega theta, and to make it identical, then I have to subtract the same thing from the adding and subtracting the same thing. Then by doing this, what we obtained is that now these terms can be combined together, and these two terms can be combined together. And then if I collect the first group, then they have the same theta and theta at the end. So they will become so omega lambda minus lambda omega multiplied by theta, and then the second term is they have the common factor of the lambda, so we can just collect them, and then omega theta minus theta omega. And then of course the definition of this one can be reduced to just the commutator, because the definition of commutator is like this. And then for the same thing, yeah, this is the definition of the commutator. So that's how we can prove this identity. And one way to memorize these commutator properties, recall the rule of the chain rule of the derivative. What do I mean by that? So, for example, if you want to find out the derivative of the fg function, then what you do is you first take the derivative of the first term. Yeah, so you do like this, multiply by g, and then you will calculate the second part derivative. So yeah, of course, for this case, this f and these are both of them are scalar value, so their order might be changed. But if you just keep the order the same, then this kind of property is simply the reflection of these relations. So yeah, this one, the first part corresponds to this, and then the second part corresponds to kind of this one. And whenever we have we define some multiplication or the addition, then we can always think about the inverse of those operations. And then we already defined the concept of the multiplication of the operator. So in that case, we might also consider about the inverse product. Well, not sorry, inverse of the multiplication. And for the given operator, if we can find this kind of operator, which uh, when this operator is multiplied to the original one, and then if they become the identity operator, then we would call this one as the inverse, which is the so that is the obvious definition of the inverse. And then one thing I want to point out is that not every operator has an inverse. And this is obvious if you think about the matrix. Not all the matrix has the inverse. So the same situation applies to the operator. And then you also learned a similar thing, like if we have the two matrix, then how can we and then if both of them if each of the matrix has its own inverse, then how can you find out the inverse of the entire thing? And then in that case, you already learned that this is the inverse, and then you can probably easily prove if you think about if you remember how you prove this matrix inverse relation. Somehow, up to now, I assume that the abstract vector corresponds to the more familiar column vector in the linear algebra, and then linear operator corresponds to the matrix. So I'm sure that you already learned those concepts, but let me just re-derive some of those facts so that you feel more comfortable with the with the notation of the abstract vectors. So more specifically, let's begin with this simplistic example which I used before. So here we have um, so we have input vector space. So maybe I should say input space, and this is output space. And then we know that each of the basis vector in the input space will map to 1 prime, and then two vector basis vector 2 will be mapped to 2 prime. Then yeah, just assume that yeah, so yeah, to give you a concrete example, yeah, let's assume that the length of this guy, this 1 prime is square root of 2. Then we can say that 1 prime is can be yeah. So we can just assume we can just use 1 prime and 2 prime as a new basis, but generally we are assuming that the input space, even though yeah, here I distinguish the input space and the output space separately. In quantum mechanics, we don't actually have two different space. So input space and the output space will be the same space. So it will be better to represent all the vectors with the same basis. So yeah, here we were just assuming some one of the orthonormal basis 1 and 2. So our goal is to represent 1 prime in terms of the 1 and 2 vectors, 2 bases. So and then we know that yeah, from here, yeah, if this one is something like this one and this one goes like this, then 1 prime is plus 1 and it is minus 2. And for the 2 prime, that is 0 times 1 plus 2, something like this. So this is some specific example, but my question is then how can we, let's see. For more concrete example, yeah, so let me also assume that the length of this one was a half. So that means that we will also have a half. something like this. Then the next question is, how can we find out this component, have 1/2 component, just using the what we originally had, some kind of abstract math? The answer is the coefficient or the vector component of some given vector in some specific basis can be found by just so this component can be obtained by um, taking the inner product between the basis and our vector in our question. And then we also know that this 2 prime is coming from this one, which means 2 prime 2 prime vector can be represented as this way. So this what this really means is that this can be written as omega um, 2, something like this. Then what about this guy? This guy also has the same logic. So it is one inner product between 1 and 2 prime, and then again 2 prime is omega 2, so that is 1 omega 2. And even eventually, um, yeah, we are using a little bit different notation, such as that this one will be written as omega. Um, yeah, I'm running out of space here. Yeah, so this one can be written as omega 2, and this one, yeah, we will also frequently use as a omega sub 1 2. And then you can also see that this component can be written as this minus 1 can be written as omega 2 1, and then also this component can be written as omega 1 1 component. So um, the transform back. So yeah, what we did was we started with the basis vectors in the original space, or initially we started with the basis, and then we apply the linear operation to each of the bases, and then we will obtain the newly mapped um, basis. Well, I should not call them as a basis, but each of the bases will be mapped to a new vector, and then that vector can be represented in the original basis. And then the relation is that if this is the new basis, um, if new vector, which I would call as a prime, and then if that vector was obtained by i's original basis, then this is written as like this one. And then um, if I rewrite, or if I expand this new vector in terms of the original basis, then the result will look like, yeah, if you look at this relation, then the um, this I will appear as the second index, second subscript, and then the first subscript is kind of dummy subscript, and then we are summing over this dummy index. Yeah, so this is the relation between the, not necessarily between, but what I'm saying is whenever we start with some basis, then the mapped result of that basis can be represented in the original basis again, and then the coefficient or the vector component will always look like this one. And now what we can do is now you know, what we can add, what we can ask is the following. So here, yeah, we only considered mapping the well-defined basis, but then what about the new vector? Yeah, so any arbitrary vector in the original space, and then this one will probably be mapped to, yeah, I don't know, yeah, maybe, yeah, let's say this will be mapped to a new vector, and then the question is, is there any relation between the input vector and then output vector, um, and then whether we can simplify the relation between these two vectors? And the answer is yes. And then yeah, let's see how we can find out such kind of relation. So we know that any arbitrary vector can be expanded in terms of the original basis. So let's say that I will just call the vector component as v sub 1 and v sub 2. And then I know that the uh, new vector v prime has is can be found by applying omega on the v. And now my question is whether yeah, whether how can uh, whether we can expand this new vector v prime in terms of the original basis. And of course, you should be always be able to find out that such kind of such kind of vector component, and it will be looking like this one. Then the question is how, yeah, what's the formula, or how can we find out this v sub 1 prime? And then the answer is v sub 1 prime can be bound by just taking the inner product between the one of the bases in the original base in the original space, and then v prime. And then we also know that this value, uh, this v prime is this one. So we can immediately say that this one, and then yeah, we have v, and instead of writing down a v like this, we can replace with this previous result, which is v sub 1 1 plus v sub 2 2. And now yeah, we know that v sub 1 is just a scalar value, so it can go anywhere. So yeah, let's just write down in this way. So yeah, this one will eventually work on this, will be applied onto the that vector, that cat. So yeah, it is v sub 1, and again, yeah, this v sub 2 can go anywhere. So yeah, this one will be will work on the 2. So it is 1 omega 2, and it is v sub 2. So this uh, new vector, and then well, the vector component of the new vector can be represented in terms of the vector component of the original vector. And then if we just try to yeah, represent the new vector in terms of the column vector, then it will be v sub 1 prime and v sub 2 prime. And then what's the relation to the original v sub 1 and v sub 2? Then yeah, it is obvious that v sub 1 can be v sub 1 prime, sorry, v prime, v sub 1 prime, yeah, it is this one. And then instead of writing in this long form, I can just use the short form, which is omega sub 1 1 v sub 1 plus omega sub 1 2 v sub 2. And similarly, this component will appear as the yeah, 2. Yeah, so it will appear as the omega sub 2 1 v sub 1 plus omega sub 2 2 v sub 2. And this one can be also rewritten as omega sub 1 1, omega sub 1 2. And the first line will be yeah, decomposed into this one. And then the, similarly, the second line will be looking like this one. So, the point is now, yeah, we know that any of the this abstract vector can be always expanded in terms of the basis, and then those vector component for this specific basis can be written yeah, if we write those vector components in the form of the column vector, and then also for the new vector, which is the result of the linear operation of the uh, linear linear operation of the original initial vector, then the vector component of this new vector can be also written in terms of the column vector. And then, so if we write all those abstract vector in terms of the column vectors, then it turns out that the linear operator by itself can be also represented in terms of the matrix. And then this matrix has a well-defined form. And then, as I mentioned, each of these component means that it is 2, 1, omega. And this one means that omega 2, 2. So it is just rewriting down the all those subscript in the front and in the back in the end. So um, even though this entire situation represent the v prime omega v, then each of them properly corresponds to these column vector and the matrix. So that's why we can say that the um, abstract vectors and the abstract linear operator can be always represented in terms of the matrix and the column vectors. And then one thing you should be really careful is that this value, specifically this omega 2, is obtained by taking the inner product uh, between this specific two bases and then two bases. So if instead of using this basis, we might consider using different bases, of course. So for example, we might consider using this basis and then this one as a new basis. Then maybe I can call it as 1 and 2. Well, okay, maybe this might be a little bit better. Yeah, if I write down this one as a 1 and 2 basis, then in that basis, this specific component will be it will be replaced by this one, and then the result of this inner product will be definitely different from this guy in most of case. So what this really means is that the same linear operator. So the linear operator, the role of a linear operator is still the same because it is mapping some vector here to this one, and this one will be mapped to here, and then eventually any arbitrary vector v will be mapped to some different vector, and then this relation won't depend on what is the basis. So whether we have this basis or this basis, this vector will still be mapped onto this one. However, each of these values, v sub 1, v sub 2, will be definitely different because this one is different because the same vector v will be expanded in terms of the Roman 1 and 2 bases with different vector components. It cannot be the same. And then again, this new mapped vector v prime, the output vector, also will be expanded in terms of the one and two Roman vectors with different vector components. So all those values, all of these values and these values will be the different, and also the matrix component will be also different. So the point is, and then we call each of these one as the matrix representation of the vector, of the abstract vector, and then matrix representation of the abstract linear operator. And then the vector or linear operator is not changing. Yeah, so we call it as an invariant in terms of the with respect to the basis. But once we represent the vectors in terms of the column vectors or in terms of the matrix, then each of these elements, the value will be different. So they will. Um, we cannot say that we cannot say that the some given linear operator will be always represented with the same value matrix with the same values. The matrix element will be always changing depending on what basis you choose, but the effect of the matrix, no, sorry, the effect of the operator will be invariant. So that is a very important concept. Okay, yeah. So I spent a lot of time on about um, the properties of the linear operator today. So yeah, let me just stop here, and then yeah, we'll continue in the next time.